All right, so today we're going to take a look at a few more examples with solving trig equations, just to get you, like I said yesterday, a feel of the different ways that you can go about it. But first, let's take a look at the homework. For homework, we asked you to solve 3 secant squared minus 2 tangent squared minus 4 equals 0. All right, so two things that are a little different. Okay, that's fine. Thank you for letting me know. Two things that are a little different. Well, we're dealing with secant and tangents instead of sines and cosines. And here we have 2 squared. Okay, before we only had 1, and there it was a little straightforward. It was a little more easier to pick how to substitute. With this one though, you could have taken one of 2 starting options. Okay, so the first thing that you have to recognize is that, well, luckily we have the Pythagorean identity of 1 plus tangent squared equals secant squared. So luckily these two are interchangeable using that identity. So we are able to simplify it in that manner. So with this part, this is where you may have differed from what I'm going to do. So you could have, and what we're going to do is I'm going to substitute in 1 plus tangent squared for this secant squared. Or you could say that tangent squared equals secant squared minus 1 and use that to replace that. Right? So either one of these would have been acceptable. I am going to replace secant squared with 1 plus tangent. All right, so this is the rule that I'm going to use. If you manipulated it and used that rule, though, okay, you're not wrong. Your process will be different, but hopefully you end up with the same answer. So rewriting this, I'm going to have 3 times 1 plus tangent squared of x, and then everything else I'm keeping the same. All right, so from here, okay, we can distribute. That's the first thing that we have to do. 3 plus 3 tangent squared x minus 2 tangent squared x minus 4 equals 0. And now we simplify. So here, because both of our tangents are squared, I can combine like terms with that. And I also have these constant terms, the 3 minus 4. So first, let's take a look at the tangents. I have 3 tangent squared minus 2 tangent squared. So 3 minus 2 is 1. So that just leaves me with a tangent squared of x. And then I have 3 minus 4. That combines to negative 1. Now we go through some basic algebra. I add 1 to both sides. And we take the square root. So tangent can be either plus or minus 1. So I'll write it separately. Tangent of x equals positive 1, and tangent of x equals negative 1. Now, some of you I did see got to this point. Good job, right? What's different about this is now we're dealing with tangent. So with tangent, and the reason that I did this was because with secant, it's a little harder. Okay, so if you did it with solving with secant, you'd end up with something similar to this. Secant equals blah, blah, blah. It's a little more tricky that way. Maybe I'll go over that after this quickly. But remember, our rule for tangent is sine over cosine. And in solving, the method that we have been using is we've been referencing the unit circle. So remember, the sine is the y-coordinate over the x-coordinate. So this requires a little bit of extra thinking. So this is telling me that when tangent is equal to 1 or negative 1, that means my x and y coordinates have to be the same. Or in this case, they have to be the same but opposite signs. So if we look at the unit circle, I should have pulled that up earlier. Give me a second. Okay, so looking at our unit circle, now I'm looking for all the terms where the x and y coordinate are equal. And that only happens 4 times. At pi over 4, at 3 pi over 4, at 5 pi over 4, and at 7 pi over 4. So at all the 45-degree increments going around the unit circle, we get, if I did root 2 over 2 over root 2 over 2, that would simplify to 1. So again, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So this actually gets us 4 answers. All right, so if you got a few of those, if maybe you only got 2 of them, okay, that's a good start. You know, if you got a little stuck, that's all right. I made this one a little challenging on purpose. All right, quickly, let's take a look at the secant version. First of all, any questions about that? I don't know.
It's good.
Okay. So then let's rewrite this. All right, so what I did here was, instead of substituting in the 4 secant, okay, I substituted in 4 tangent, right? So our rule was tangent squared equals secant squared minus 1. All right, so that's what I put there instead. So if we do it this way, okay, again, be careful. Make sure you distribute everything. Combining like terms, I get positive 1 secant squared minus 6 equals 0. So I get secant squared of x equals 6. So here, this is where we get into a little bit of trouble. I don't have a reference for this. Okay, even if I did my rules, well, first, I mean, I guess I could take the square root, but that doesn't really help us. Did I write that right? Yeah. All right. And then, I mean, I can say that, well, I can't break down the square root of 6. So I don't have any way to reference this on the unit circle. What I could do is I can change secant into 1 over cosine. But then I get an even stranger solution. Okay, if I did the reciprocal on both sides, I get cosine equals plus or minus 1 over the square root of 6. And then if I did the fancy rule, okay, I don't have this anywhere on the unit circle. All right, so in this case, we would have to use inverse trigonometry. And it'd be a little trickier to get those answers that we got. Right. So, you know, my recommendation is work with sine, cosine, and tangent because they're a little more manageable. Right. And it'd be a little trickier right? You'd have to plug this into the calculator. And then you wouldn't get the answers with the pi. You'd get decimal answers. So be careful with that, right? So yeah, my recommendation is try to work with the three main trig functions, sine, cosine, and tangent. And if it can only be sine and cosine with those two, that's even better. Okay? All right, so let's look. We got a few more different examples, and then we can be done with this part of solving. We did the squaring. Okay. So a topic that we're going to be talking about a little bit more in the future is something called multiple angles. Now, maybe that's a little fuzzy. Let me see if I can focus. Yeah, that's better. Okay. What it means to have a multiple angle is when we have something other than an x or a theta or a t with our cosine. So if I have the problem two cosine of 3 theta minus 1 equals 0. Okay, this part here, that's what's considered multiple angles because we are multiplying our variable inside with the cosine, right? But this actually isn't as tricky as it sounds. We're just going to go through our basic algebra steps. Right? Again, I want to get this theta alone. I want to isolate the theta, so I work from the outside in to get that by itself. So the first thing I have to do is add 1 on both sides. And then I divide by 2. So I don't need it on that side anymore. Okay. So when we get to this point, I still can't touch that 3 because it's kind of tied inside with the cosine on the outside. All right. So remember, again, when we work algebraically to solve, we do opposite operations, inverse operations, working from the outside in. We have to chip away from the outside before we can get to the variable on the inside. So my next step here would be getting rid of that cosine. So when I'm just gonna replace this right now. When does cosine equal 1/2? All right, so this is your basic rule. Maybe you've memorized this by now. If not, we can reference the unit circle. Right, cosine is the x value. When does it equal positive 1/2? So we have a pi over 3 and then 5 pi over 3. All right, so normally if I just had cosine equals 1/2, these would be my solutions. But it's not cosine of x, okay, it's cosine of 3 theta. So what I'm going to do is what I did here was I did substitution. I said, let's say 3 theta is equal to some variable x. So now I'm going to resubstitute. So this becomes 3 theta equals pi over 3 plus 2 pi n. And this one becomes 3 theta equals 5 pi over 3 plus 2 pi n. Okay, did I lose anybody there? Switching in between that and there. Okay, I just used this x as a placeholder just so it wasn't as confusing. I could have done this whole thing with the 3 theta, right? But I just didn't want you to get tied up with this 3 theta when all I was worried was, well, when does cosine equal 1/2? Okay, so this 3 theta could go here, here, and here, but I just replaced it with the x to make it a little more simple for this first time around. So then I have to go back and I have to resubstitute. All right, so that's how we end up here. So with this shows that I'm not done yet. Okay, what I have to do is I have to divide by 3. So my answers now, right, I have to divide everything by 3. So pi over 3 divided by 3 becomes pi over 9. Plus, now this, I don't have anything to combine this with, so I'm just going to write 2 pi n over 3. All right, so I just distribute that divided by 3 to both of those parts. And I do the same thing over here. So this is going to become 5 pi over 9 plus 2 pi n over 3. So when we have that multiple angle, that's telling us we're going to have an extra step at the end to make sure we isolate the variable. Okay, before we didn't have anything else on the inside. It was just, you know, like a cosine x or cosine t or whatever. But if you have something on the inside of the cosine or sine or tangent, all right, that's telling us that we have to take it an extra step at the end. And that's what we did there. Okay, it might be x over 2, right? So you might be dividing on the inside. So if that happens, in your last step, you would multiply everything by 2. All right. I don't want to spend too much time on this, though, because later on, next week or the week after, we have some special rules with multiple angles that make things a little easier for us. But there, you can do it this way as well. All right, any questions about using multiple angles or solving with multiple angles? All right, one more example, and then we've kind of summed up all the different ways we can solve. Now, this one's a bit of a stretch, and you're not going to see it much. It's not very a common way to solve, but I would like to show it to you. All right, so we want to solve sine squared x minus 3 sine x minus 2 equals 0. And what this means is that x is going to be in between 0 and 2 pi. So I don't have to worry about doing this extra stuff at the end. Whatever answer I find, that'll be my answer. All right, so let's go through what we have before. Well, everything is in sines, right? So even though I have a sine squared, I don't want to change it to cosines because this is sine. So I don't have to use my Pythagorean identity. There's no other identities I can use. Sine is pretty basic, so we're going to leave it at that. So it looks like we have somewhat of a quadratic situation going on. So if we try to split it up, we encounter a problem. Because this is -2, and this is -3, there's no combination that I can get that'll get that. All right, none of this work. Normal factoring does not work. So going back to algebra and algebra 2, the only other way to solve a quadratic equation that you can't factor or solve in any other basic methods we can use the quadratic formula. All right, so just as a quick recap. All right, that is our quadratic formula. I'm sure Miss Nunez made you sing a song about it, so hopefully you remember it. Now, our only difference is instead of just x being the solution, our solution is going to be the sine of x. So we still have our A, our B, and our C. That's just the numbers in front. Okay, so A is just 1 because there's nothing in front of that. B is -3. That's my middle term. And my constant term C is -2. So we're just going to plug these into the quadratic formula. So I have -3, so that gives me a +3, plus or minus -3 squared, minus 4 times A, which is 1, times B, which is -2, all over 2 times 1. Okay, so we simplify inside underneath the square root, and I get 3 plus or minus the square root of 17 over 2. And that is equal to sine of x. Now, when we are using this method, when we are doing the quadratic formula, there's no way I'm going to find this on a unit circle. Okay, so one second. Okay, right. It's this some complex, not complex because it doesn't have imaginary in it, but it's a difficult quotient with a radical. It's a messed up number. So in this instance, we have no other option other than to use a calculator. Right. So just be careful when you're plugging this in. So you're going to do the inverse sine of 3. Actually, let me do another parentheses. 3 plus the square root of 17. And then I'm going to close that parentheses for the numerator, divided by 2. And there's an error. What did I do? I don't know what I did. Oh, I know what I did. There's an error in the domain because this answer, if I do 3 plus 17 square root of 2, is greater than 1. We cannot take the inverse sine of a number greater than 1. So this one doesn't work. So I don't have to worry about the plus. All I have is the minus. So let's change that to a minus. Okay, so that's an interesting answer, especially because we're talking about radians. So I'm going to go back and look at that. I was not in radian mode, so I make sure I'm in radian mode. And I retyped the solution. Okay, so I get -0.59. Now we're going to keep it like this. I'm not worried about making this into pi. But my problem here is I want my answer to be in between 0 and about 6.24. Okay, but this is negative. So remember, what we can do is we can add 2 pi to this for one full rotation, right? Because, if I was looking at the graph, -0.59 radians might be somewhere down here. So if I add 2 pi to it, I end up in the same spot. That's going to be about 5.69, we'll say. Okay, and then I'm going to say radians because I don't have a pi in there. All right, so that was a little different, a little trickier. But like I said, it's not a very common situation that you'll find yourself in solving for that. So I'm not going to give you homework on that, but I did want you to see that it is possible to use something like the quadratic formula in order to solve trigonometry. And I'm just going to rewrite this real quick just to say. All right, that's the setup that we did. And again, we didn't choose the positive because then that would give us something greater than 1, and we can't take the inverse sine of anything greater than 1. Okay. So yeah. All right. So yeah, tomorrow we're gonna start with some newer stuff. Like I said, we're wrapping up with trig. We still got a little trig left, but we're getting close to the end. Actually, I'm not alive. I forgot about this. Okay. Anyway, yeah, we'll start something new tomorrow. And yeah, have a good day. I'll see everybody tomorrow.
Bye, Mr. Murray.
Bye-bye.